In this lesson, we're going to talk about slope, rates of change, and linear functions. It's really important to review the slope and rates of change and really understand what that means so that when we go later on in the course to study derivatives, we have a good solid foundation in order to understand what a derivative is. So slope and rates of change is very important to understand in order to understand what a derivative is. So we're going to start off with that. Now, just to recall, I'm sure you guys have seen this before, and this should be just a review, but the slope is the ratio between the vertical change and the horizontal change. And there's different ways that you can label it. A lot of people will label it as M. Sometimes you'll see change of Y over change of X. Another way you might see it is the difference in the Y's over the difference in the X's. So these are the different ways that you can denote slopes. Now let's talk about the different kinds of slopes that we could have. Slope tells us two things about a linear function. It tells us the steepness of the line, and it also tells us the direction that the line is tilted. When we look at the slope, we have a sign in front of the slope, whether it's negative or positive, and then we have some number. I'm going to label that as just n. N is some number. The positive or negative tells us the direction that the line is tilted. If it's a positive, you're going to see the line increase from left to right, and you always want to read a graph left to right, just like you're reading a book. So when you look at it left to right, if it's increasing, it's positive. If it's decreasing, it's negative. The value of the number tells us how steep the line is. The bigger the number, the more steep the line is. So looking at these three examples down here, this line here is a negative slope because as I just traced it, going left to right, it's going down. This one here that's labeled as a positive slope, as I trace it, it goes up. So remember, you have to trace it left to right. Now this slope here is 0 because that line neither increases or decreases. So we call that a 0 slope. Now there's another special case that is not included in the slides that I want to add in. So I'm going to make some room down here. So here's our axes. And if I have a line that's vertical, that's called an undefined slope. And we'll get more into that later. Now here's another interpretation of slope. It's a geometric interpretation. If you're looking at this line and you have 2 points, P1 and P2 on this line, if you look to see what the difference is in the y's and then divide by the difference in the x's, then another way you can look at that is called the rise over run. If I want to go from this point to this point, I would find the vertical distance and then divide that by the horizontal distance. So now we're going to look at the first example, and it says find the slope of the line y equals 2x plus 3. And there is a couple different ways that you can identify the slope of a line. You can identify it from the equation of a line in a form called slope-intercept form. The m, or the slope, is the coefficient of the x. So in this case, 2 is my slope. When it's in slope-intercept form, the number that doesn't have the x is what's called the y-intercept, and that's where it crosses the y-axis. So it crosses right here at -3. So from looking at the equation, we identify the slope as 2 and the y-intercept is -3. If we want to identify the slope from the graph, then we're going to do that geometrically. The author has picked 2 points for us to use. However, if you need to pick your own, I highly suggest to make sure you pick points that cross exactly on an intersection of the grid. For example, if I choose this point right here, I'm not sure if that is exactly 0.5 for my x, or if that's 0.4, or if that's 0.6. It's really hard to tell if it doesn't cross on an intersection of the grid exactly. So to make sure that you get the correct answer, make sure that you pick points where it crosses exactly at an intersection. Okay, so the author of the book shows the 0.21 on the line and the 0.45 on the line. So when we do this geometrically, we want to look at the change for the vertical distance. So that's from here to here. So that's going to be 4. And then we want to look at the horizontal distance from here to here, and that's going to be 2. And then once you get your vertical change and your horizontal change, you take your vertical change and divide by your horizontal change. So that's going to be 4 divided by 2, which is 2. You also want to identify what the direction of your slope is, because sometimes students accidentally put a negative in there where it shouldn't belong, or a positive where it doesn't belong. And so you want to make sure that you have the correct sign. Because we divided 4 divided by 2 and got a positive 2, I verified that by tracing the line left to right, and as I go left to right, it's going up, so it's a positive. If it was going down left to right, I know I made a mistake and I got to double check. Now let's look at example 2. It says find the slope of the line through the point -2, -3, and -5, 1. We're going to use the formula of the slope now. So it doesn't matter which point you call the first point or the second point, as long as you're consistent. What I mean by that, if you're calling this x1, this has to be y1. If you call that -2, x2, then this has to be y2. The 2's and the 1's need to line up or need to be with the same coordinate. As long as you keep the 2's and the 1's together in your formula that match with the points, then it's going to come out the same no matter what. So it looks like the author of the book made this the first point and this the second point. So this is x1, y1, x2, y2. So when you look at your formula, you're going to take the change in your y's. When you do this, you also have to be consistent with the way that you're subtracting. If I subtracted and took y1 minus y2 and x1 minus x2 on the bottom, if I switch those 2's and 1's, as long as I'm consistent, my answer is going to be the same. But I can't subtract y2 first here and then x1 down here. They have to line up. It's because subtraction is not commutative. If I take 4 minus 3 and then 3 minus 4, we're going to get 2 different answers. So you want to make sure that you stay consistent with that. So this is my y2. I take 1 minus, and also be careful with your negatives. You might get a double negative where it changes into a positive. There's a minus in the formula, and this value also might be minus. Okay, so here's our y1. So that goes in here. So I have 1 minus, this is my y1, so that's a -3, which makes that a positive, which is a 4. And then when I take x2 minus x1, that's a -5. That's my x2. This is my x1. So I take -5 minus a -2. This negative and this negative become a positive. And so I have -5 plus 2, and I get a -3. So my final answer for the slope of the line that passes through these 2 points is -4/3. That negative tells me it's going to be slanted so that it decreases left to right. Now, if I plot these 2 points on the grid, here's -5, 1, Here's -2, -3, and we can check the slope geometrically. So if I look at the vertical distance, so I'm going, here's my vertical point here, 1 to -3. That distance is 4. When I go and look at the horizontal distance, that distance from here to here is 3. So that's geometrically where we're getting the 4/3. And then because it decreases left to right, we have to make sure that there's a negative there for the slope. In example 3, we have find the slope of the line containing 3, -1, and 3, 4. We're going to use the definition for slope, and we're going to get, here are these 2 points here, 3, 4, and 3, -1. When we use our formula, because 3, which is our x coordinate, it doesn't change. It's going from x equals to 3 to x equals 3. So when we subtract, since there's no change, we're going to get a 0 in the denominator. And we all know when we get a 0 in the denominator, that is not defined because there is no number that I could take times 0 and get -5. However, if I had 8/4, that's equal to 2 because I can take 2 times 4 is equal to 8. So this case, it's undefined. And this is one of our special cases that I talked about at the very beginning of the lesson. When you have a vertical line, it's undefined. Now, when I go to write the equation of this line, because the x's stay the same no matter what the y value is, the equation for a vertical line is going to be x equals, and then whatever that x value is, in this case 3. Because no matter what point on that line we look at, the value of x is always going to be 3. Now the same idea applies to a horizontal line. If you look at a horizontal line, no matter what, you're always going to see that the y value of a horizontal line is the same, which is why horizontal lines always have the equation y equals, and then whatever the value is for y that it passes through on the grid. In the next example, example 4, we're going to talk about specifically modeling slope and rate of change. Now, a lot of times when we're working with graphs or equations of lines, and they're not in a context where those quantities of x and y represent anything specific, it's just some generic value. When we apply slope to an application, then we get more information from slope because those x's and y's actually represent some quantity in real life. It says on the chart below, find the slope of the line connecting the first point, which is 1955 and 0.29, with the highest point of 2005, 2.93. And we're going to explain the significance of the result. If we look at the graph, notice that this graph represents fuel economy, so the average price per gallon for each year, and the years are marked down here. And the years are marked down here on the horizontal axis. So Y represents dollars and X represents the year. So we have specific quantities that are assigned to X and Y. It's not just some generic number. So if I take the slope between this point and this point, it's going to be more than just a number. It's going to actually represent something that we can interpret. So we're going to take 2.93 and subtract 0.29. And then we're going to divide that by 2005 minus 1955. When we work this out using the order of operations, we are going to get 0.0528. Now, because this isn't on some generic grid and we have actual quantities assigned to the variables x's and y's, we have to interpret this. What in the world does this number mean? 0.0528. What does that mean in the context of this application? Remember what this value means. It's our slope, so it's the change in y over change in x. When I look at the change in y, let me label it here, change in y, change in x. When I look at the change in y, that's going to represent dollars, the change in the amount of dollars. And when I look at the change in x, that's going to be the change in the years. So this right here, when we interpret it, is going to be 0.0528 dollars per year. Because this is a positive, this means it's an increase in $0.0528 per year. So if I connect these two lines with the dot, or sorry, these two dots with the line, imagine that my line is actually straight. If I look at that line that passes through those 2 points, we have that it changes from 1955 to 2005 at an average rate. It's not a specific rate, it's just an average rate of $0.0528 per year. Later on in the course, we're going to talk about instantaneous rate of change. So average rate of change is the change between 2 points on average. What happens? There's a lot of different stuff that happens in here, but on average between these 2 points, this is the change. Later on, we're going to talk about instantaneous. What is happening exactly at that point? Now, if we look at 2 other points, let's look at this point and this point. If I find the slope of the line that passes through those 2 points, although it's a pretty bad line, let me try to fix it here. All right. Going from here, my hand isn't very steady. That's a little bit better. So we're going through this point and this point here. I'm going to let you guys do the intermediate steps for practice, but when you find the slope of the line that passes through those 2 points, you should get negative 0.038. And because our x's and y's are assigned to quantities, we need to interpret it. So again, because we're taking the change of y over the change in x, we're going to get that this represents dollars per year. Now, because this is negative $0.08 per year, that tells me that it's a decrease in price from 2005 to 2010. And you can visually check that when you look at the slant of that line. That line is slanting down left to right. In example 5, we're going to work on another application. Rather than using y's in our formula for slope, we're going to use function notation. And then also we're going to work with a restricted domain because in the context of this question, it doesn't make sense to go outside the interval of 0 to 2. The situation is that we have some girl named Kendra. She tosses a softball into the air with an underhand motion. The distance of the ball over her head is given by the function symbolic form. H of t is equal to 32t minus 16t squared when t is between 0 and 2. It says find the average rate of change of the function from 1/4 second to 1 second. T represents the seconds, and even though it didn't say that in the problem, we can see that based on the graph here. Time is our input or our independent variable, and our distance, our height in feet, is our dependent variable. So we have to find the average rate of change of this function between 1/4 and 1 second. And we're limiting the domain from 0 to 2 because it doesn't make sense to go past 0 to the left because that would be negative seconds and that doesn't make sense. And then we're not going past 2 to the right, bigger than 2, because when you graph it, you'll see that it hits the ground at 2 seconds. So this is where she starts at 0 seconds, the ball comes up, and then it comes back down and it lands at 2 seconds. If we pass 2 seconds and go to 3 or 4 seconds, and I continue along the quadratic, that's going to give me a negative height, which again doesn't make sense in this example. So that's why we're limiting the domain from 0 to 2. So let me get out my pen. We need to find the average rate of change, which is a fancy way of saying slope. Okay, so we're going to take the difference in the y's. So we have 2 points here. We have the independent variable, that's our 1/4. And then our corresponding y value, using function notation, would be h of 1/4. So that's our first ordered pair. Our second ordered pair, we start for our input or our independent variable as 1, and then our dependent variable or the output is h of 1. This is going to be like our x1 and our y1, and this is going to be our x2 and our y2. So we're going to take h of 1 and subtract h of 1/4, and then we're going to divide that by 1 minus 1/4. Now, to find our corresponding dependent value, I got to plug 1 in here and find out what that height is. And remember, the height is in feet. Notice that over here. When you work that out and you divide by the difference between 1 and 1/4, you're going to get a slope or an average rate of change of 12. Now, to interpret what that 12 means, the change in y is distance, which is feet. So that's going to go on the top. The change of x goes on the bottom, and that's the change in time in seconds. So this 12 represents velocity. That's our average rate of change of 12 feet per second. Now, if I pick another 2 points on the graph, like maybe right here and right here, I'm going to get a similar slope, but it's going to be different because that line is tilted differently. And then if I pick another 2 points and I find the slope from here to here, that's going to give me a negative slope. So when you're looking at a curved function or just some generic curve in general, and you're finding the average rate of change, depending on the 2 points you pick, your average rate of change is going to be different. But if you're looking at a line, no matter what 2 points you pick on that line, the slope is going to be the same. So linear functions have a constant rate of change. And when we look at curves, that rate of change is going to be different depending on the 2 points that you pick. I would interpret this as the ball rises from a time of 1/4 second to a time of 1 second. The average height is changing 12 feet per second. In this example, we're going to talk about an application where a balloon that's being inflated, the surface area is changing with respect to the radius of that sphere. So it says a balloon in the shape of a sphere is being inflated. The formula for the surface of the balloon is S of r is equal to 4 pi r squared, and r is going to be greater than 0. Because r is the radius, it doesn't make sense to talk about negative radius. So r is going to be greater than or equal to 0. We're going to find the average rate of change in the surface area of the balloon as the radius increases from 1 to 3. When we set up our formula for rate of change, which is the same as the slope, we're going to take the dependent variable, s of 3, and we're going to subtract s of 1, and we're going to divide that by 3 minus 1. This here will give me my corresponding value with 3 for that coordinate. This will give me my corresponding value for 1 for this coordinate. So when I do that and I work it out, I'm going to get 16 pi as my rate of change. When we're looking at it on this graph, here's when I have a radius of 1, here's when I have a radius of 3, and so 16 pi represents the slope of this line that passes through those 2 points. So the slope of this line here, which is our average rate of change, is 16 pi. Our interpretation with this one is a little unusual. When I look at my quantities, what they represent, my dependent quantity is my surface area. And when we're talking about surface area, area is 2-dimensional, so it's going to be something squared. And then here it says that's in inches. So the top quantity that's changing, or our y value that's changing, our change of y, is going to be inches squared. My change in the radius is going to be in inches. Like the radius is just a distance from one point to another, so that's 1-dimensional. So I'm only going to have inches to the first power. So that's going to go down here. This is a little bit unusual because normally what we want to do when we have units like that, we want to simplify it. And I'm all for simplifying all the time. However, in this case, it's a little bit unusual. If I simplify that to just inches and I cross off an inch on the top and the bottom, this is going to be very hard for someone to interpret what that means in terms of the surface area changing. That's a little bit unusual. So in this case, I would not simplify. I would leave it as it is, and I would say that the surface area with the units inches squared is changing with respect to the radius, the length of the radius in inches. The final interpretation would be for every inch that the radius increases, the surface area increases by 16 pi. Now that we've had quite a bit of practice with slopes, average rate of change, and how we apply that to real-world settings, we're going to keep up that idea of average rate of change, but we're going to transition it to a more general approach. What we're about to talk about now is going to lead us into the differences between secant lines and tangent lines, which will then help us learn about limits, which will then help us learn about derivatives, and then integrals. So pretty much everything in calculus is based on this. So it's really important. Now, this expression here is called the difference quotient. Is it any different on how we calculate slope or rate of change? Absolutely not. You're taking the difference in your dependent variable and divide by the difference of your independent variable. We're just going to look at it in a more generic fashion. So we have this curve right here, and it's listed as f of x. Then we have this blue line that's going through the points P and Q that are on that curve, f of x. So just like we did before, when we find slope, we take the difference in our vertical values, that's this, which is this up here, And then we look at the difference in our horizontal change. So that's this. This line here is what's called the secant line. And this is when we have a line that passes through 2 points on some curve. Tangent lines is a line that passes through just 1 point on the curve. It literally just touches it in that 1 point. So that would be a tangent line, and that's what we're leading up to. So the difference quotient is really just a way to represent the average rate of change between 2 points on a curve, A and B. Now, when we were discussing the previous slide, I mentioned that the difference quotient is a way to find the rate of change generically. And so these two examples are a perfect way to explain that. Now we're going to look at it generically where we're not actually plugging in specific values. We're going to set it up in a way that we can plug in whatever we want. We're going to set it up like a function. Here's our f of x, and our difference quotient is taking the y value for the second point and subtracting the y value for the first point, and then doing the same thing with the x's in the denominator, finding the change of x. So in this example, we don't have specific x values, we have generic x values. So I have the first point as x1, and then f of x1. Then I have my second point as x2, and then f of x2. We are going to take f of x2 minus f of x1 and subtract x2 minus x1. When we use our function to do that, I'm going to find f of x2, I'm going to take x2 and plug it into the function. That's what we always do when we're looking for a corresponding y value. We plug in the value of x. That's our x2 in this case. I'm going to have x1 now. When I plug in x1, I'm going to get 3 times x1 minus 5. So here's our generic value of x. Here is our generic value of y. Then when we do the same thing with x2, we're going to have x2. And then when I plug in x2 in here, we're going to get 3x2 minus 5. Now, when we put that together here, where I take the difference of my dependent and the difference of my independent, we're going to get 3x2 subtract 5. That's my f of x2. And we're going to subtract 3 of x1 minus 5. And then divide by x2 minus x1. So it looks a little bit weird, but all we're doing is generically stating if I plug in this value of x, whatever that is, x2, in here, this is my corresponding y value, and same thing with the x1. And then from here, we just have to simplify it. So if I take 3x2 minus 3x1, this is what I've got. If I take this -5 and subtract this -5, these two negatives here are double negative, so it makes it a plus. So I have -5 plus 5, so the 5's disappear. Then on the bottom, I have x2 minus x1. Now, if I factor out a 3, the x2 minus x1 divided by the x2 minus 1, the x2 minus x1 divided by the x2 minus x1 will divide out to be 0, and I'm left with 3. If we look at this, if you're really comfortable with average rates of change and slope, we could have avoided all of that work that we just did up here, because this function that's given to us is a linear function. And no matter what 2 points you pick, you're always going to get the same slope because the slope is constant. So without doing all this work, I knew ahead of time that my answer should be 3. That's our slope. However, that doesn't always work if you have something that's curved. That only works for linear functions. So for this example down here, we're going to do the same thing. I'm going to plug in x2 and x1 into our function and use the difference quotient to find the generic rate of change, and then we're going to simplify it. If I put x2 into this function here to get my corresponding value, I'm going to have x2 squared minus 4. Then when I plug in my x1 to find my corresponding value, I'm going to get x1 squared minus 4. And then this is my f of x2 minus my f of x1. That's all in the numerator. Then in the denominator, I'm going to take the difference of my x's. So that's going to be x2 minus x1. Now, when I simplify this, I get a minus 4 minus a minus 4. So this minus 4 and this 4 turns into a plus because I got a double negative. The 4's disappear. And so on the top, I'm left with x2 squared minus x1 squared all over x2 minus x1. Now, I can keep simplifying because x2 squared minus x1 squared is the difference of squares, and we know how to factor that. When we factor it, it's x2 minus x1 times x2 plus x1. And that's all over x2 minus x1. And then this factor can cancel with that factor, and I'm left with x2 plus x1 as my generic average rate of change. So if I wanted to find any average rate of change for any 2 points, let's say x1 is 7 and x2 is 3, I would know my average rate of change is 10 because I just add these together. Now that we've got slopes and average rate of change down, we're going to look specifically at equations of linear functions. So we have, and I've already talked about this a little bit, and this should be review for you guys, but there's the slope-intercept form of the equation of the line. That's when you have y equals mx plus b, where m is your slope and b is your y-intercept. We can define a linear function by saying if the function can be written in this form, where I have some coefficient times x and then plus a constant, then that would be considered a linear function. Looking at example 10 and example 11, these should be pretty easy. It says find the equation of the line with a slope negative 4/3 and a y-intercept of 5. So here is our slope-intercept form of the line. So since this is the slope, which is equal to m, we're going to plug that in here. And since the y-intercept is our b, we're going to plug that in here. And then we get the result here of y equals negative 4/3 x plus 5. We're asked to find the slope and y-intercept of a line, but it's not given in slope-intercept form. When we're looking at slope-intercept form, it's easy to quickly identify what the slope and the y-intercept is. The slope is whatever is in front of the x, and the b is the constant. So to identify the slope and the y-intercept, we are going to solve this equation for y and put it in slope-intercept form. So we have 2x minus 3y is equal to 5. To solve for y, I need to first get rid of this term with the x in it. So I'm going to subtract 2x from both sides. Now, to finish isolating y, we're going to get rid of the negative 3 by dividing both sides by negative 3. You can either write it as negative 2x plus 5 quantity all over negative 3, or you can separate it like this. When we separate it like this, then it makes it easier to identify what the slope in the y-intercept is. The slope is 2/3 because that's the coefficient of x, and our y-intercept is negative 5/3. Now this one, for example 12, says graph the linear function negative 2/3 x plus 2 using the slope and the y-intercept. What we need to do is first start with the y-intercept. Because this 2 is the y-intercept, for sure we know we have the point 0,2 on the line. So you plot that. Now, because we know that the slope is negative 2/3, we know that every time x moves 3 spaces, y moves 2 spaces. And this negative tells me which way it's tilted. So every time x goes 3, 1, 2, 3, y goes exchange of 2, 1, 2. So here's another point on that line. And when I draw the line through the 2 points, I can see that it has a negative slope. So I make sure that I tilted it in the right direction. Now, when we look at point slope form of the equation of a line, and all you need in order to put an equation in this form is the slope, and we need one point, any point, and we'll label it as x1, y1. So you put in 1 point here, that's for your x point, and then your y point goes here. Find the equation of the line with a slope of negative 2 that contains the point negative 4, 3. So using this right here, my slope is negative 2, so I plug negative 2 in for that m. Then we're given the point negative 4, 3. So negative 4 goes in for x1, 3 goes in for y1. That's this here. Now this turned into a plus because we have a negative in the formula, but then also 4 was negative. So that made it a double negative that changed it to positive. Here is our point slope form of the equation. From here, if we wanted to, we could put it in slope intercept form. All we have to do is expand this and solve for y. If I distribute the negative 2, I get negative 2x minus 8, and then I just add 3 to both sides. So now I can identify not only the slope, but we knew that to begin with because that was given to us, but now we can identify the y-intercept. In this example, we're given 2 points, but not the slope. So we're going to have to do a little bit more work to find the slope. So we have these 2 points here. To find the slope, we're going to take y2 minus y1, which gives us a double negative. And then we have x2 minus x1. So I end up with 4 over negative 6. And when we simplify that, we get a slope of negative 2/3. When we put this in point slope form, we can use either point. It doesn't matter. Since both of those points are on the line, no matter what I put in for x1 and y1, we're going to still get the same answer. So it looks like the author of the book chose to use this point here when he plugged it in for x1, y1. So the negative 2/3 goes in for the slope. And here we put the x1, so that's our 3. So we're going to subtract 3. And then over here, we're going to put in our y1, which is negative 1. So I have y minus a negative 1, which makes this a positive. So here is our point slope form. Now, if we distribute the negative 2/3 and subtract 1 from both sides, then we can put that in slope intercept form. So I can see that my y-intercept is 1 and that my slope is negative 2/3. However, we found that out up here when we calculated slope. If this comes out different down here than the slope that we found, somewhere you made an arithmetic mistake. You should go back and check. Now, here's a little note over here, which is exactly what I was talking about when we were picking a point to plug in. The author of the book chose to plug this point in for our point slope form. However, we could have plugged this point in and still gotten the same line. When we plug in our slope right here, we get -2/3. But then if we use the point -3, that means I got a +3 here because I'll have a double negative, and then I'll have y -3 here. This line looks different than this line, but it's not different. If you solve this for y and put it in slope-intercept form, you're going to get the same answer. So the takeaway from this is that if you have 2 points, it doesn't matter which one you pick when you plug it into your point slope form. So in the first part of our lesson, we really focused on rates of change and difference quotient. And we put an emphasis on the fact that for both of those, we're really just calculating slope and we are just looking at it from different perspectives. So now what I want to do is sum up the linear equations, and I want to focus on the special cases. So for the examples below, we have m as the slope, and then a and b are real numbers. When we look at our first special case, we have some slope times x, and then even though it's not written in there, we have a +0. And that tells me that the x and the y-intercept are both 0 because it crosses on the y-axis at 0, which means it also crosses at x equals 0. So we have a slant line with x and y-intercepts both 0. Our next special case, and when we talked about this previously, we were really focused on the slope, but we briefly mentioned what the equation looks like. So when we have a vertical line, the slope is going to be undefined because there's no change in the x value. This right here is not necessarily true. So you might want to make a note. There is a time when you can have y-intercepts, and it's going to be the entire y-axis. If this vertical line actually lies on the y-axis, then every point on that line is going to touch the y-axis. So in a sense, you're going to have infinite y-intercepts. Now, because the value of x doesn't change here, that's what causes it to be an undefined slope, because the change in x is going to be 0, which means when we calculate slope, the change in x is 0 is going to be in the denominator. For a horizontal line, that is when the slope is 0 because it's not increasing and it's not decreasing. And again, I'm not a big fan of the fact that they put that in there. Most of the time that will be the case. But if this line falls on the x-axis, then every single point on that line is going to be an x-intercept. So that's a special case of the special case. The y-intercept is going to be whatever point here that it crosses through on the y-axis. And our equation is going to be y equals b, because no matter where we are on that line, the y value is always going to be that constant, and the x value is going to be what's changed. For the last topic of this lesson, we're going to talk about a kind of function called a piecewise defined function. And a piecewise defined function is when you take bits and pieces of other functions over a specific domain and you put them together on a grid to create a new function with the pieces together. Sometimes those pieces meet up and sometimes there are gaps between those pieces. Also, you can have 2 pieces, 3 pieces, 4, it doesn't matter, it's just going to be 2 or more. For this kind of function, the notation looks like this, where you have an f of x, but you define it with each piece. So we're going to use part of the function x plus 1, which is a linear function, but we're only going to use the part of that graph that lies on the interval that x is less than or equal to 1. The second piece of this function that we're going to use the constant function, f of x is equal to 3, but we're only going to use that piece when x is greater than 1. Here's our linear function, x plus 1, graphed. But if you notice, it's only graphed when x is less than or equal to 1. So here's 1 on the x-axis. So less than or equal to 1 means it's only going to be graphed to the left of x equals 1. And because on this piece we're including the point 1, we're going to have a closed circle to indicate that there's a point there. Now, when we look at the second piece, that's our constant function, f of x is equal to 3. So that's going to be a horizontal line, but we're only keeping the piece that lies on the interval x is greater than 1. Notice this isn't including 1. So we're going to graph the line. If you imagine the entire function graphed, it would be this whole entire line, but we're only keeping the part that is greater than 1. And because 1 is not included, we're going to draw an open circle here to show that there's no point there. To point out something important, when you're trying to determine if it's a function by using the vertical line test, if you have pieces of that function that overlap, that's where you might have a concern. And if that vertical line goes through it in more than one place, then it fails to be a function. However, since there is no value here, but only here, when I do the vertical line test, it only passes through one point. So this passes as a function. If this was colored in and I included 1 here in the domain, then when I did the vertical line test, it would pass through 2 points so that it would fail as a function. Let's look at the next example. A way that you can use piecewise functions and when you have situations that you need to break into different intervals. So in this example, it talks about a college sorority that's organizing a fundraiser dance. Now the author goes on to explain that tickets are going to be sold for the fundraiser dance for $20 each. It also says, if you look down here, there's a maximum of 350 people that can fit in this facility that they're renting for the dance. It also tells us here that the cost of the rental for that one night is $100. This application is asking us to build a piecewise function that shows the profit based on what interval you're going to fall on. Now, the two intervals are going to be based on how many people are going to be at this party. If you read more into this, it says if there's more than 150 people, then they require a security guard. But if they're less than 150, they do not need to pay for a security guard. So when we figure out the profit function, we have to break this up into, do we need a security guard or not? Because if we do, that's going to be an additional cost. So we have to split that in 2 pieces. So this first piece here is going to be based on not needing the security guard. So this is going to be based on if the number of people that come is between 0 and 150 inclusive. To figure out the profit function, if you don't have to pay for the security guard, then it's going to be $20 per ticket. And if we let X be the number of tickets sold, that's going to be 20 times X for our profit, but we still have to pay for the rental. So we take off $100. And this will give us our profit for the fundraiser. If there's more than 150 people, then they're going to have to pay for a security guard. So that's going to be on the interval when X is greater than 150, but less than or equal to 350. It's stated in the problem that this facility can hold 350 people, and that's it. So they're not going to go over 350. So in the case where the number of people is greater than 150, then we also have to pay for a security guard. So our profit function is going to be different. So it's going to be the 20x, right, times the number, 20 times the number of tickets. But then we have to subtract off not only the facility rental, but we have to subtract off the amount for the security guard. So that's 100 and then another 150. So we'd have to subtract off 250 if the number of people fall between 150 and 350 inclusive. When you graph this, this is the picture you're going to see. Now, because these are pretty close, the author of the book chose to zoom in so you can see what this looks like. So these are both lines, but they're going to have different y-intercepts. This is the second piece because we're not including that 150, so that's going to be open. The first piece is represented by this part of the graph because we have 150 as a closed circle for this interval. And when we look to see if it passes the vertical line test, it passes through this point, but there's no point here, so it does pass the vertical line test. So this right here is this zoomed in so that you can see what it looks like. It says use the function and graphs to find the domain of this function. The nice thing about when you have a piecewise graph is that the domain is literally stated for you right here. So the domain, all the values from 0 to 350, including 0 and including 350. If I write it as separate intervals, that's fine, but because 150 is included here, then the interval goes from 0 to 350 without skipping over any points for the x. So you can write it down separately, or you can combine those intervals together since there's no gap from 0 to 350. Now, if we're looking for the value of P, the profit, when the number of tickets sold is 145, and we want to use our formula to find that value, then we have to make sure we're looking at the correct piece. 145 falls on this first interval, which is this piece of the graph right here. So when I plug in 145, I'm going to put the 145 in right here. So you would take 20 times 145 and subtract 100, and that would give you a Y value or a profit of 2,800. For this one right here, you have to be careful. This is one of our endpoints. If I want to figure out which piece of the function I need to plug in that 150, because I see 150 here twice, I have to pay attention to the details. 150 is included on this interval because it's less than or equal to. It's not equal to 150 here, so I want to make sure that I plug it in to this first piece here. So I'm going to take 20 times 150 and subtract 100. That would give us a profit of 2,900. The last part, part D, we want to find the profit when the number of tickets sold is 155. Because 155 lies on this second interval here, I want to be sure to plug it into this piece of the function. So I'm going to take 20 times 155 and then subtract 250. That is going to give us a profit of 2,850. The next couple of examples, I want to go through and show you how you can use GeoGebra to do two things. One, I'm going to show you how to use GeoGebra to graph a piecewise function. And you're basically just going to graph it the same way, but just state the restricted domain for each of those pieces. The next thing I want to show you how to do on GeoGebra is how to use GeoGebra to find the average rate of change to save you some arithmetic work. So to graph a piecewise function, I'm just going to make something up. Let's say I want to have 3 pieces. The first piece I want to be a constant function. I want it to be the constant function 5, but I want to restrict it to the domain of, let's say, x is greater than 7. Whoops, I forgot my comma. Okay, so there's my line, y equals 5, but it's only graphed from 7 and up. Whether or not I put x is greater than or equal to or greater than, it's not going to show me an open or closed circle here. So I have to make sure that I understand what is at that endpoint. Let's say I want the next piece to be x squared, and then I'm going to put a comma and then state my restricted domain in my parentheses. Let's say I want to do that between 0 and 7. So I'm going to put in there that 0 less than or equal to x, which is less than or equal to 7. So let's zoom out a little bit. So we can see that my quadratic x squared goes from 0 to 7 and then it stops. Now, even though I put the equal sign here, it doesn't show me a closed dot, so be aware of that. Let's do one more piece. Let's do the square root of negative x, and then I want to put a comma and then put my restricted domain. So when you zoom in, you can see that these pieces meet up. Sorry if I'm making you motion sickness here. These two pieces, the quadratic, which is blue, and then the line, which is green, don't meet up. But this one does. Since I put the domain here, x is greater than -1, it's going to start at -1 and go to the right. However, this function already has a restriction domain. It can't go over 0 because once I start putting in positive numbers, then I'm going to get a negative under the square root. If I put in 2, I'm going to get the square root of -2, and then that's not going to get graphed on the real plane. So really, I could have put in it's greater than -1, but less than or equal to 0, and that would have still given me the same picture. The next thing I want to show you is how to find the average rate of change on GeoGebra so that it does the arithmetic for you. So looking at this blue piece, the quadratic x squared, let's say I want to find the average rate of change from 1 to, let's say, 2.5. So the quadratic function is g of x. And when we find the average rate of change, we're basically finding the slope. So I'm going to do g, and then I'm going to put of 1 minus g of 3. Oh no, we said 2.5. Let's go to 2.5. And I'm going to put this in parentheses. Right now it's calculated the numerator, but now I'm going to tell it to divide by 1 minus 2.5. When I hit enter, it's going to give me the average rate of change from 1 to 2.5 because I've already defined these functions so that it does the work for me. For example 18, I'm going to show you how to graph a piecewise function by hand. Now there's different ways that you can do that. However, after doing this for so many years, I have perfected a method that makes it fairly easy. What you need to do is make sure you make a t-table for each piece of the graph. So I'm going to call this piece number 1 and this piece number 2. For each of those, I'm going to make a t-table. So this is the t-table for the first piece of this function. When you are making your t-table, because a lot of the times you have functions that are curvy in here, like x squared that has a curve to it, you want to make sure you use at least 3 points so that you can graph the curve as accurately as possible when you draw that on the grid. The more points that you have, the more accurate that's going to be. You also want to make sure that when you plot the points, you stick to this interval. This quadratic function is only going to be graphed on the interval where x is less than or equal to 2. And you certainly want to make sure that when you're picking your points, you use your endpoint as well. So I'm going to start with 2 because that is my endpoint here. And what I like to do, because this says x is less than or equal to 2, I like to draw a little closed circle next to that point to remind me when I draw this on the graph as one of my endpoints that it's going to include that 2. So we're going to plug in 2. I get 2 squared, which is 4, minus 4 is 0. Then I'm going to go less than 2. I'll pick 1. So when I plug 1 in here, I get 1 squared minus 4. That's going to give me a negative 3. Then I'm going to use 0. When I plug in 0, I get negative 4. So on one end of this interval, I have a closed circle 2. On the other end, because it's less than 2, I'm going to draw an arrow. So I'd like to label that as well. Now for the second piece, now I'm looking and plugging things in here. This has values of x that are greater than 2. So we're going to plot 3 points, and I'm going to make sure I use my endpoints. This has an endpoint of 2, although it's not included. So when I put 2 down for x, I'm going to put an open circle there to remind me that 2 is not included. And then I'm going to pick values that are greater than 2, let's say 3 and 4. And then because it's greater than 2, I know I'm going to have an arrow go into positive infinity. You can even label that. This is going to positive infinity, and because this is less than, this is going to go to negative infinity. When I plug in 2, and I'm making sure that I plug it into the right piece, I'm going to get negative 2 plus 2, that's 0. When I plug in 3, I'm going to get negative 3 plus 2 is negative 1. And when I plug in 4, I'm going to get negative 4 plus 2 is a negative 2. So now I have everything I need to graph this. For the first piece, which is a quadratic, I'm going to graph the point 2, 0 and make sure that's a closed circle. So here's 2, 0 right here. Then I'm going to plot the point 1, negative 3. Then I'm going to plot the point 0, negative 4. Now I know that this is a quadratic that is concave up because my leading coefficient is positive. So I know it's going to look something like this, just as a rough sketch. If you want to be even more accurate, and I suggest that especially with things that are curved, you want to plot some more points over here. For the second piece, it's a line, and I'm going to start with 2, 0. The point 2, 0 should be an open circle because that is not including 2. Now this one's interesting because I have an open circle overlapping a closed circle. So I have this and this that are overlapping. When you have an open circle that's overlapping a closed circle, it's going to remain closed. If you have an open circle overlapping with an open circle, then it's going to remain open. So I have this point on my line, then the next point is going to be 3, negative 1. Then I have the point 4, negative 2. Although it's not very straight because my hand is not steady, this should be a straight line. There's my piecewise function. This is the quadratic piece, and this is the linear piece. Now, to sum up the things that you should be able to do when you work on your homework, these are the big points. Describe the behavior of a line with a negative slope. You should be able to describe the behavior of a line with a negative slope. You also want to do that with a positive slope and then your special cases of undefined or a 0 slope. The second part says, would you rather climb a hill with a slope of 1/2 or a slope of 3? Explain why. So part B of this is really getting at making sure that you understand how to read the slope and understand the steepness. So a half is going to be less steep than a 3. Part C says, what is the difference quotient? The difference quotient is just a generic way to find slope, because rather than plugging in values, you're plugging in 2 random values of x. So once you simplify, you can plug in any 2 points on that function and find the average rate of change. Part D says, describe how you would find the equation of a line if you knew the slope and the y-intercept of the line. So part D is getting at being able to determine a good format for the equation of a line depending on the information that's given to you.